All right. So now I want to talk about a different class of defects in ceramics because these are ones that are non-stoichiometric. So everything we've talked about so far, Schottky, Frenkel, is what we call stoichiometric. They don't change the ratio of metal, non-metal, cation, anion ratio. However, these defects do. All right. So basically these types of defects, these non-stoichiometric, do not preserve stoichiometry. So if we're looking at something like iron oxide, which I've showed here, if we had a Frenkel or a Schottky defect, that would preserve the FeO ratio that we would see with this type of crystal. However, an example of a non-stoichiometric defect would be one where we have a Fe2 plus vacancy. So that's the black iron 2 plus that we see. So there's a vacancy here. And so obviously that creates a charge. And so to counter that, we also have the substitution of these iron ions for a different valence, so Fe3 plus. So two of those substituted for the 2 plus would balance the missing charge that we have from the Fe2 plus. So this is one way in which we could have this non-stoichiometric defect. And it occurs in a crystal like this, where something like iron has multiple valences possible. So because iron can be 2 plus and 3 plus, this type of defect is possible. Others it may not be. So that's the example of what we have here. So let's just kind of look at this in a little bit more detail. So we have the inclusion, presence of these 3 plus. So that means that we put in, if we put in one Fe3 plus, that's another way of looking at it, right? That would basically cause a positive 1 charge to the overall crystal. So that would mean that we'd have to potentially remove something with a positive charge. And so we can do that, and the only positive charge we can delete is a cation. And so we can delete Fe2 plus. However, that's plus 2. So if we get rid of that, we would actually have to have another Fe3 plus in order to compensate. So if we just kind of work through the math, is what I have down here is, basically getting rid of one of those iron 2 plus would require 2 of the 3 plus with a net plus 1 charge each. And so that's how we kind of balance it, and we have a vacancy. But the other thing to consider here is that because of this, the overall amount of iron in this structure relative to oxygen has actually gone down, right? So there should be an iron here in the typical structure, but now we have one less. And so we can actually write this as Fe1 minus XO, right? So it's basically iron deficient in this case. And so this is actually pretty common in multiple valent oxides, where we have something like a transition metal, which has multiple valent states. We can have a structure like this from something like this, where we have differences in valencies, which causes a vacancy in the cation. Let's also look at the charge balance when we could have something like an impurity or something doped into the structure. So let's look at sodium chloride. So we have Na plus, Cl minus. So this is basically without impurities. But let's look now if we have calcium 2 plus instead of the sodium, right? So if we're going to exchange these, they have different charges, right? Sodium has a plus 1, calcium has a plus 2. So in order to exchange that, we would actually have to exchange 2 sodiums for every calcium. And so if we did that, then that would also mean that we would have to have, so we would basically get rid of 2 of those cations, so this one and this one, for example, and replace it with 1 calcium, which is what you see over here. So that means that we have less cations than we did before. To balance the charge, we basically have to get rid of a sodium in this structure. If we look at it the other way, let's look at oxygen for chlorine. So same thing, chlorine has a -1, oxygen has a -2. So we would have to have 2 chlorine for every oxygen that happens. So we would get rid of these 2 chlorines like we have here and here, and then exchange it with 1 oxygen to balance the charge. But again, the stoichiometry of this crystal would be different now, right? Because here we have less anion, up here we have less cation, right? So the impurities can often cause non-stoichiometric defects as well. And these are just a couple of examples, but you can envision many scenarios where we have differences in charge causing these non-stoichiometric defects in ceramics.